Welcome to the Explainer. Today, we're taking abstract mathematical theory and turning it into a concrete, real-world narrative about the actual mechanics of sorting data. I'm absolutely thrilled to guide you through this because we're going to look under the hood of the very systems that literally organize our entire digital world.
So think about this for a second. Every single time your favorite travel app organizes a list of flights by price or your photo gallery sorts thousands of pictures by date, how does the computer actually pull that off? How does it juggle millions of data points in mere milliseconds? And maybe even more intriguingly, is there some unbreakable universal speed limit to how fast a computer can possibly do it? Today, we're taking a journey from the core mechanics of basic sorting straight into some mind-bending, rule-breaking plot twists that computer scientists actually use to cheat that very speed limit.
Section 1. Divide and Conquer, the core philosophy.
To understand how modern sorting achieves such incredible speeds, we have to start with the foundational engine powering it all. Imagine you have a massive, totally unwieldy problem. It's like trying to sort a completely shuffled deck of 10,000 playing cards. Doing that all at once? Absolute nightmare. Divide and Conquer steps in and says, don't. Instead, you physically split that massive problem into tiny, manageable, constant-sized chunks. You divide the input data. Then you conquer those subproblems recursively, meaning you just keep splitting them until they're so small they're basically already sorted. And finally, you combine those solved tiny pieces back together into your final solution.
And that brings us to our first major contender in the sorting race, merge sort. Merge sort takes this divide and conquer philosophy completely literally. Step 1. You literally just chop the sequence straight down the middle into two halves. Step 2. You recursively sort both halves. Just keep chopping until you're staring at individual elements. Then step 3, you conquer by merging those smaller sorted halves back into one unique, fully sorted sequence.
Now think about that final, crucial merging step. You have two already sorted sequences, S1 and S2. Because they are already sorted individually, we don't have to go crazy and compare every single number to every other number. We just look at the first item of each sequence. 2 is smaller than 3? Okay, 2 goes first. Then we compare the next ones, 5 and 3. 3 is smaller, so 3 goes next. Honestly, merging these sequences feels exactly like seamlessly zipping a jacket together. You just walk down the lists, picking the smaller of the two front elements. Because of this, the merge step operates in linear time. We literally only have to look at each element basically once to zip them together.
So, here is the absolute magic of this strategy. Because we divide the sequence in half every single time, the number of times we can split it before hitting single elements is logarithmic. If you draw it out, the recursion tree has a height of log n. At each level of that tree, we do linear work, O of n work, zipping those lists back together. Multiply the height of the tree by the work done at each level, and boom, you get merge sort's guaranteed running time, big O of n log n. In the computer science world, that is incredibly fast and highly scalable.
But yeah, there's a catch. As fast and reliable as merge sort is, it has a critical real-world limitation. When you're zipping those sequences together, you can't just do it in the original space without overriding your own data. You need extra space, auxiliary memory, to hold the newly merged sequence before copying it back. If you're sorting a massive data set that barely fits on your computer's RAM, doubling that memory requirement just to sort it, that might literally crash your system. We need a memory-saving alternative.
Section 2. Quick sort and in-place sorting.
Meet the randomized, memory-efficient sibling. Quicksort approaches divide and conquer with a totally different strategy. Instead of blindly chopping the list in half and doing the hard work at the end during the merge, Quicksort does the heavy lifting before the split. First, you pick a random element from the list. This is our pivot. Then, you swiftly partition all the other elements relative to this pivot. It's exactly like splitting a deck of cards relative to a target card. Everything less than the pivot goes to the left, everything greater goes to the right, and equals stay in the middle. Then you just recursively do the exact same thing to the left and right sides. Because you already did all the sorting work during the partition, joining the results at the end literally takes zero effort.
But what makes Quicksort an absolute heavyweight champion is its ability to do this partitioning in place. It doesn't go and create brand new arrays for the less than or greater than piles. Instead, it uses two indices, a left and a right marker. The left marker scans forward until it hits an element that belongs on the right, and the right marker scans backward until it finds one that belongs on the left. When they both find one, they simply swap elements directly within the original structure. This brilliant little technique means Quicksort requires virtually zero extra memory.
Pitting them head-to-head, we see some fascinating trade-offs.
Merge sort gives you a rock-solid, guaranteed big O of n log n time, but it totally taxes your memory. Quick sort gives you this incredibly elegant, in-place memory usage, but its time is an expected O of n log n. Because quicksort relies on a random pivot, if you get terribly unlucky, like picking the absolute highest or lowest number every single time, it can degrade to a much slower n-squared time. But mathematically speaking, thanks to the laws of probability, quicksort's expected time is O of n log n, and its super low memory overhead very often makes it the faster choice in actual practice.
Section 3. The sorting speed limit. Is there a wall?
Okay, we've hit O of n log n twice now. Are we just not smart enough to find a faster algorithm, or is there a fundamental physical limit to how fast we can sort? To answer that, look at how both of these algorithms actually work. They completely rely on asking questions. Specifically, is item X less than item Y? Every time an algorithm asks that yes or no question, it branches down a path in a decision tree. To properly sort n items, that tree has to have a leaf for every single possible output permutation. And for n items, there are n factorial possible orderings. Because a binary tree with n factorial leaves must have a certain minimum height, the math strictly dictates that the worst-case number of questions you must ask is the logarithm of n factorial. And through mathematical approximation, the logarithm of n factorial simplifies to n log n. I really want you to let that sink in for a second. Omega of n log n is the universal speed limit. It is mathematically impossible to write a sorting algorithm that relies on comparing elements to one another that runs any faster than n log n in the worst case. The universe literally will not allow it.
Which logically sets us up for the ultimate plot twist of this whole explainer. Can we sort faster than O(n log n? If the math says absolutely no way, is there a loophole? Well, the answer is yes. But to do it, we're going to have to completely abandon everything we just learned about comparing items.
Section 4. Radix-sort, breaking the rules.
We are officially entering the wild territory of non-comparison-based sorting. Think about it. If you never ask, is x less than y, the n log n speed limit suddenly doesn't apply to you at all. But before we break the rules, we need a special tool called a stable sort. The stable sort property means that if you have two items that are essentially tied, like two playing cards that are both 7s, their relative order from the original unsorted list is perfectly preserved in the final sorted list. The one that came first initially still comes first. This is absolutely crucial if you want to sort complex data layer by layer without totally ruining the work you just finished on the previous layer.
The most famous stable sort that doesn't use comparisons is called bucket sort, and honestly, it's almost hilariously simple. Imagine you're sorting numbers from 0 to 9. You just set up 10 literal buckets, numbered 0 through 9. In phase 1, you look at your data. If you see a 7, you don't compare it to anything, you just drop it directly into bucket number 7. The value itself literally becomes the physical address. In phase 2, you just walk from bucket 0 to bucket 9 and pull everything out sequentially. You used 0 external comparisons, you just place things in their pre-designated spots.
But you might be wondering, what if you're sorting huge numbers, like 32-bit integers or really long strings? You obviously can't just create 4 billion buckets. That's where Radix-sort steps in. Radix-sort elegantly chains bucket sorts together. It handles complex items dimension by dimension. So for numbers, it starts by bucket sorting everything using only the lowest rightmost digit. Because bucket sort is perfectly stable, when Radix-sort runs again on the next digit to the left, it perfectly preserves the order of the previous digit. It just sorts layer by layer in lexicographic order, working from the lowest bit all the way up to the highest.
Bam, there's your loophole. Because we never once directly compared two items, we completely bypass that decision tree limit we talked about earlier. The time complexity for bucket sort is big O of n plus n, where n is the number of items and n is the number of buckets. For Radix-sort, you just multiply that by d, the number of dimensions or digits you're checking. It's totally shocking, but this time complexity is strictly linear. Under the right conditions, these non-comparison sorts successfully break the n log n speed limit entirely.
So let's look at this grand finale comparison. It perfectly wraps up the mechanics, the math, and the utility of everything we've explored today. We've got merge sort, your guaranteed rock-solid O and n log n workhorse that unfortunately requires the bit of extra memory. We have quick sort, the super elegant, randomized, in-place champion that software libraries absolutely love. And finally, Radix-sort, the stable, non-comparison rebel that achieves linear time by completely rewriting the rules of engagement. Which leaves us with one final thought. These aren't just abstract math concepts on a whiteboard.
They are the physical realities running inside the microchips of your devices right this very second. Every time you hit sort by price, one of these incredibly clever paradigms wakes up and goes to work. So now that you actually understand the divide and conquer mechanics, the brilliant memory-saving tricks, and the absolutely ingenious loopholes of non-comparison sorting, which algorithm do you think is running under the hood of your favorite app right now? Thanks for joining me on this explainer.